Friends, I will tell passive reinforcement learning. To keep things simple, we start with the case of a passive learning agent using a state-based representation in a fully observable environment. In passive learning, the agent's policy means it is fixed. In state 8, it always executes the action in 8. This goal is simple to learn how good the policy is, that is to learn the utility function U8. We will use as our example the 4.14 to 3 word introduced in chapter 17. Figure 21.1 shows the policy for that world and the corresponding utilities. Clearly, the passive learning task is similar to the policy evaluation task. Part of the policy integration algorithm described in section 17.3. The main difference is that the passive learning agent does not know the transition model P8 or 8A, which specifies the probability of reaching state 81 and the state 8 after doing action, and nor does it know the reward function R8, which specifies the reward of each state. Figure 21.1a, a policy warner for the 4 into 3 world. This policy happens to be optimal with rewards of R bracket S 0.04 in the non-terminal states with no discounting B. The utilities of the states in the 4.3 world given policy warner. The agent executes a set of trials in the environment using its policy warner. In each trial, the agent starts in state 1 bracket 1, and experiences a sequence of state transitions until it reaches one of the terminal states 4, 2 or 4, 3. It perceives apply both the current state and the reward received in the state. Typical trials might look like this. As you can see, okay, note that each state perceived is subscripted with the reward received. The object is to use the information about rewards to learn the expected utility U8 associated with each non-term INA state 8. The utility is defined to be expected sum of the discounted rewards obtained if policy warner is followed as in the equation on the page 650 we write. You can see the equation where R bracket S the reward for a state, st a random variable, is the state reached at time t when executing policy warner. So equal to S, we will include a discount factor 1 in all of our equations. But for the 4x3 world, we will set 1 equal to 1. Direct utility estimation. A simple method for direct utility estimation was invented in the late 1950s in the area of adaptive control theory by Woodrow and Hoff 1960. The idea is that the utility of a state is the expected total reward from that state onward, called the expected reward to go, and each trial provides a sample of this quantity for each state visited. For example, the first trial in the set of 3 given earlier provides a sample total reward of 0.72 in the state 1, 1. The two samples of 0.76 and 0.84 for 1, 2, two samples of 0.80 and 0.88 for 1, 3, and so on. Thus, at the end of each sequence, the algorithm and updates the estimated utility for that state accordingly, just by keeping a running average for each state in a table. In a limit of infinitely many trials, the sample average will converge to the true expectation in the equation. It is clear that the direct utility estimation isn't just an instance of supervised learning where each example has a status input and observed reward to go. as output. This means that we have reduced the reinforcement learning to a standard inductive learning problem, as we discussed in chapter 18. Section 21.4 discusses the use of more powerful kinds of representations for the utility function. Learning techniques for those representations can be applied direct to the observed data. Direct utility estimation succeeds in reducing the reinforcement learning problem to an inductive learning problem about which much is known. Unfortunately, it misses a very important source of information, namely the fact that the utilities of states are not independent. The utility of each state equals its own reward plus the expected utility of its successor states. That is the utility values obey the Bellman equation for a fixed policy. See also equation 17.10. You can see the equation 17.10. Okay, now by ignoring the connections between states, direct utility estimation misses opportunities for learning. For example, the second of the three trials given earlier reaches the state 3,2, which has not previously been visited. The next transition reaches 3,3, which is known from the first trial to have a high utility. The Bellman equation suggests immediately that 3,2 is also likely to have a high utility because it leads to 3,3. But direct utility estimation learns nothing until the end of the trial. More broadly, we can view direct utility estimation as searching for U in a hypothesis space. That is much as learning for U is a hypothesis space that is much larger than it needs to be, in that it includes many functions that violate the Bellman equations. For this reason, the algorithm often converges very slow. So tomorrow I will tell about supervised learning. So tata friends, please subscribe, like and comment this channel. Okay, if you like this channel, then also share with your friends. Thank you.